Hi, welcome to Chapter 3, Chemical Reactions and Reaction Stoichiometry, Part 1. So the first thing we have to talk about are chemical equations. Chemical equations are like a recipe to a chemist. They represent chemical reactions on paper. When you have an arrow separating it, the items on the left of the arrow are your reactants, and the items on after the arrow are your products. The plus sign just means that they are being reacted to each other. A balanced equation follows the law of conservation of mass. That is why you see there are these coefficients here. So the mass on one side of the arrow has to be equal to the mass on the other side. So when you're balancing, you only add coefficients. You cannot add a subscript. Over here is an illustration of why. Here we needed to balance our waters. If we added a coefficient, we have 2 water molecules. But if you just add a subscript, you have 1 molecule of hydrogen peroxide. Which is a totally different compound. Some other important symbols in chemical reactions are the states of matter, where G is for gas, and S is for solid, L is for liquid, and AQ is for aqueous, meaning dissolved in water. The triangle on top of the arrow means that it was heated. So your chemical reaction not only tells you what you're mixing and what you're making, but it tells you the states that it's in. And down here are all of the abbreviations and what they mean. There are 6 types of reactions, and it is important to notice the pattern in the chemical reactions because that'll help you when you want to predict the products and then balance your reaction. The first one is a combination reaction where you start with 2 items and you equal, and you come together. So A plus B, and you make C. So 2 things come together to make 1. The opposite of combination is decomposition, where you start with 1 and you break it apart into 2 pieces. Then you have single replacement, where you have an element and a compound. And the element will take the place of one of the elements in the compound. So here you see the A and the B are switching places. Double replacement, you have 2 compounds and you end up with 2 new compounds. Combustion reactions are when you react something with oxygen. And in particular, we're going to look at hydrocarbons plus oxygen. And when you are combusting hydrocarbons, you're always going to produce carbon dioxide and water vapor. And last is oxidation and reduction reactions, where you're actually changing the oxidation states or charges. So here's combination reaction. So you see here, A plus B, you'll see that is our pattern that we're looking for. If you have 2 elements, it's kind of easy to predict the product. So you have to look at your periodic table, find their charges, and then crisscross and write your products. So here you have carbon plus oxygen making carbon dioxide. And this last one here, you see you actually have 2 compounds coming together to make 1 compound. So combination is not just 2 elements coming together. It could be 2 compounds. So here, let's see if we could do this example. So we have magnesium. If you look at the periodic table, magnesium has a +2 charge, reacting with oxygen, which has a -2 charge. So you're going to make magnesium oxide. Now this is not balanced. So you have to go and balance the reaction. And I don't know if you remember doing this in class, but when you burn it, you make a bright light and a white powder, so it's a solid. Decomposition is the reverse. You're taking your compound and ripping it apart into two substances. And so here is your pattern again. And here are some examples. Sometimes the two substances you're ripping it apart into are two elements, or it could be two compounds. For example, down here is a decomposition of a metal carbonate. All metal carbonates will make metal oxides plus carbon dioxide gas. So that is a rule that you'll have to remember. Okay, and again, this triangle here means that you heat it. So if you heat calcium carbonate, you'll make calcium oxide and carbon dioxide gas. Single replacement, again, you have your single element replacing one of the elements in the compound. In order for this reaction to occur, the single element must be more reactive than the element it is replacing. So on this table here is your reactivity or activity. So the higher you are, the more reactive. So this is most reactive. And actually this is two tables kind of combined. So your reactivity increases as you go up. These are for the metals. These are your metals. And these are your nonmetals. So in our example here, we have iron reacting with copper sulfate. So you find iron on this table and copper. So you see iron is higher than copper, so it's more reactive, so it will actually bump the copper out and take its place. So you get solid copper and iron sulfate. Double replacement, again, you have two compounds making two new compounds. And in this case, you have to look at most of your double replacement reactions are occurring in aqueous solutions. So when you write your products, you have to look at a solubility table, which I included here for you, to see if you form a precipitate or not. In this illustration here, the copper 2 hydroxide is your precipitate, that's your solid, and the sodium sulfate is aqueous. So here are your solubility rules and table. Combustion, again, it's when you heat it up and react it with oxygen and produce carbon dioxide and water. This is for hydrocarbons. So you see here, you have your CH4, you have your oxygen molecules, you heat it up, and you're making carbon dioxide and water. So that is your combustion reactions. And that is the end of part 1.